As I've been commuting quite a bit the last days, I've been looking around for some papers to implement while on the train. And Jay Grice pointed me to this one, which is a really nice and short paper about visibility calculation for a point set. That means a point cloud only, for example, something that comes out of a raw 3D scan. And what this whole paper is, it's basically a giant hack. So let's go over what the guys are doing here. Basically what this algorithm does is it takes some unstructured point clouds and tries to find out which points are facing towards the camera and which points are occluded by other points, the geometry, so to speak, to come up with something like this, which makes the whole point cloud thing a bit more readable to the user in the viewport. And what this paper came up with is called an HPR operator, a hidden point removal operator. And the way this operator works is it's kind of a hack, using a bit of geometry combined with a convex hull algorithm in order to figure out which points are facing the camera and which points are occluded. The first bit of geometry trickery is this here, and it's called spherical flipping. In this case in the paper, it's shown in 2D, so we are taking this blue image of a cat here, and we position it in our scene so that the camera is sitting at the world origin, so 0, 0, 0, and it's looking out at this cat here. Next, we're trying to figure out which is the point that's farthest away from our center, so from our camera, which in our case is this, and we're going to draw a circle in 2D or a sphere in 3D around our geometry. And then we use this circle or sphere to flip the points along the surface of this circle or sphere. So this cat here, when it's flipped on this sphere, becomes this weirdly squished geometry here. Now, here comes the trick or the fun part about this algorithm. We now turned this outer border of the cat into something that is convex. So all of those points of this outer hull will be found by a convex hull algorithm, and when projected back, will form the backside of this cat. What this means is basically feeding this flipped geometry here into a convex hull algorithm, together with the center point, will result in the fact that all points that are visible to our camera are part of this newly created convex hull. So all we have to do to determine the visibility of our points is A, do this spherical flipping, then pipe those flipped points into a convex hull algorithm, and check which points are part of the newly created surface of our convex hull algorithm. Luckily, Houdini provides us with all the tools needed to implement that, and it's a really quick one and a really fun one, I think. So let's get cracking. In Houdini, first I want to use some geometry to work on. In our case, I'll just use the trusty old pig head, drop that down, dive in there, and I'll just set this to easy, maybe subdivide it once, like this, and scatter some points onto the surface. In fact, those will simulate the points that came in through a 3D scanner. Maybe increase the point count a bit to, say, 30,000, like so. And we can see those weird intersections here, and we have no proper idea in which direction the pig head is looking now. Let's add a camera in here, because what we want to do is we want to move this geometry around so that the camera will be the center of our scene, and the geometry will be moved in respect to that camera. So what I need for that is I need the camera translation here, so let's right-click on that, click on Copy Parameter, and then dive into our test geometry here, drop down a transform, right-click on the translate here, go to paste relative reference, let's drag this down a bit and check invert transformation, wire in our scattered points in here, and now we have those points translated, transformed, as if the camera were our null point at the center of our scene. To later build a correct convex hull, I want to add a single point at the center point here, so for example let's use an add sop here, and just check the single point and merge it together with our geostream. So now when we highlight point display, we can see we have a single point here at the center and our point cloud for the pig head. Next we need to find out which is the farthest point from the center here, and I'll do that using an attrib angle and a bit of vex. Drop down an attrib angle, set it to detail, so we'll only run through this once. And in here, first thing I'm going to do is I'll create a float variable, call this one d for distance, and set it to -1. Something rather small. And now I want to run over all my points in that mesh, so I'll use a for loop for that. Let's initialize it with a variable called npt, set that to 0, which is the first point in our geostream, and we want to increment this as long as npt is smaller than our number of points in that geostream. And we want to increment this by 1 each iteration, like this. So far, so good. Next, for each iteration, let's just get the point position, call this one npos, and we're going to use the point function, looking up p, the position, at our point with the point number npt. So we're iterating through all the points, basically. Next, let's get the distance of this point to the center by just creating another variable, call it nd, and using the length function to measure the length of our position vector, like this. And now we want to check if nd, so our new distance here that we just measured, is bigger than our current biggest distance, d, stored in this variable here. And if it is so, then d equals to our new distance here. And also, we will write out this to a detail attribute called maxd for maximum distance. So when we let that run and head into our geo spreadsheet, go to the detail attributes here, we can see we have now a maximum distance of 5.47 something. Let's just have a quick look at our paper. And this paper gives this equation here for the spherical flipping here. So we're basically interested in this part here. And the only thing that needs a bit of explanation are the variables. So pi is the point position, r is the sphere radius, basically our max d that we just calculated, and then those weird operators here and here. And what they are the norm of our point position. And what the norm is in 2D and 3D space is it's just the length. So basically the length of the vector pointing to our point position. So let's just put that on one side of our screen and Houdini on the other side, drag this over a bit and create another point triangle down here and do the spherical flipping here. So we'll run this over points, and first we need to get r. So let's call this float capital R, and it should be equal to our detail attribute that we just stored, called maxd. And now let's implement this formula here. So it says pi, that's the point position, equals to pi plus something. So we can write that as v at p plus equals. Then we have 2 times this bracketed formula here. So 2 times capital R minus the norm of our point position. Basically this is the length, so we want to calculate this only once. So let's use another variable for that. Call it LP for length point. And it's the length of our current position here, like this. So R minus LP, got that, times, I want to use brackets again, V at P, that's PI, divided by LP again, which is the length of our point position, like that. So you can see now we get this weird distorted pig shape here, which kind of looks right, looks like it's working. So next we want to use a convex hull algorithm to build a convex hull consisting out of these points here. And we can do that by using Houdini's built-in tetrahedralize SOP here, which has a mode called convex hull. We'll just output the polygons. And also we want to uncheck remove unused points. So this will keep points that are not used in the convex hull. Let me explain why. So we can already see we are building this convex hull out of all of our points. And next, using another point triangle, we will check in our original geostream and the tetrahedralize geostream. We will check if any of these points coming in through the original stream is part of the surface of this newly created convex hull. And we'll do so by checking if our point is part of a primitive. So let's do that by using the pointPrims function, which will return the list of primitives of which a point is part of. So we want to look for point primitives on our second input slot. That's the one with the ID 1. So we're looking for primitives on this tetrahedralize here at our current point number. And this is the reason why we unchecked remove unused groups. So we keep our point numbers consistent in both geostreams. Next, we'll just get the length of this array called prims, write it into a variable hasPrim. And now we check if hasPrim is equal to 0. So if a point is not a member of a primitive and thus not a member of this tetrahedralized surface, then we'll remove the point. Let's check if that worked. And yeah, we removed quite a bunch of points, but our pig head geometry is still distorted. So let's reset those points that we didn't remove to their original position. And in order to do that, we first have to store our original position here. Before we modify and flip this, let's just save an attribute called rest with the undistorted position. And after we deleted those points, let's reset the position to their original rest position, like so. So after we've done that, finally let's get rid of this transform here again. So transform it back by just copying this transform node and just attaching it down here. This time unchecking invert transformation, so the pig head should be at its original position again. So now let's have a look through the camera which we used. And we can see this algorithm was a bit eager of removing points. It removed quite a bit more points than we actually wanted. And when looking at this paper here, The way the authors got rid of this problem or tackled this problem is with a user-tweakable parameter, which adjusts the radius of the sphere on which we are reflecting those points. And the way that's implemented is up here, where we are flipping. When we are calculating the flipping sphere's radius here, we multiply this radius with a factor. And in the paper, they used the power function to raise 10 to the power of some user-tweakable parameter, which they called capital R2. So let's just create that. And let's increase this parameter here. And we can see we can now dial in how many of those points are visible. And usually I've had quite good success with values around 3. So now we are getting a decent clipping, a decent culling of points here. Also, let's adjust this slider's value range by going up here to the cogwheel symbol, clicking on Edit Parameter Interface, and then on the slider here, let's set that in a range between 0 and 6. Hit Apply and Accept. So we can now dial in this manual parameter of how many points we want to cull away. Let's just lock the camera and move around here a bit to check if our algorithm is working. And yeah, indeed it is. So let's talk a bit about how and why this adjustment of the radius and the visibility of the point works. And for that, let's uncheck the locked camera and highlight the tetrahedralize that we used to build our convex hull. So you can see this is quite a big geometry here. This goes off into the distance. Actually, when we middle mouse on this, we can see we're having a size of 66,000 by 45,000. So this is really huge. So in order to see what's happening, let's scale that down using a transform. Wire this in and highlight it. And you can see this is the convex hull that our algorithm built. And for some reason, there are many points of this pighead that are part of this convex hull. So let's just copy these 3 nodes here and dial in a smaller value of R, maybe 0. So the tetrahedralize doesn't need scaling now because it's very, very small here. And now we've got less points which are part of the surface here. Why? Well, when we look at this node here, what's happening here, with smaller values of R, our geometry gets distorted quite a bit when we regard this as our mirror sphere or mirror circle. However, if we increase this value here, this R value, you can already see our geometry gets kind of squished towards the spherical surface. And the bigger this R value, the closer all of our points of the geometry get pushed towards a spherical surface, which for our tetrahedralize and our convex hull algorithm means more and more points lie on this spherical convex surface. So the higher our R value, the stronger we're pushing our points onto a spherical surface, and the more points land on our actual convex hull. And as this is the only criteria we're checking when deciding if we're going to remove a point or not, the more our original geometry is deformed towards a spherical surface, the more points we are keeping. So, in my opinion, that's a really neat geometric hack. And it's a really clever way of using and abusing Houdini's built-in tools such as the convex hull algorithm in conjunction with a bit of Vex. Also, this paper is a typical example of something that's actually quite easily understandable, and the paper does a decent job at explaining what it does actually. It also offers some pseudocode, so if you want to start implementing papers, this one might be a neat one, as it's really quickly to implement, the math is not that elaborate, and as long as you have a decent convex hull algorithm at your disposal, it's actually not much work to implement. And the output, admittedly, is quite impressive. I mean, this is a view-dependent culling of points that are not connected in any way, so it opens up a neat way of working with point cloud data, in my opinion. Alright, hope you had fun with this, and until next time, it's cheers and goodbye.